Okay, quadratic form first. I think it is worth to cover during the class, since I hope you guys get accustomed to these two processes. Okay, one of the proposition is that if Q is a real symmetric matrix, also Q is a square matrix, all of its eigenvalues are real numbers. Okay, so let's assume x is a complex number a plus bi, and s bar is conjugate of this s, a minus bi. Then we know that s times t conjugate is s conjugate times t conjugate, right? If S is real, if and only if S is right, that's straightforward. In another word, S multiplied by S bar is A squared. Okay, so if lambda is an eigenvalue of Q for some eigenvector which is not 0, then from this definition of this eigenvalue, we can write Qx is equal to lambda x for non-zero x, and Qx conjugate is conjugate of lambda x, which is also same as Q conjugate x conjugate lambda conjugate x. Okay. It's just straightforward. Okay, now x transpose Qx Can you follow this step? Another thing is we can write Qx is lambda x, and x conjugate transpose Q x is equal to x conjugate transpose lambda x, right? And since lambda is scalar, a real scalar value, we can write this lambda in front of this. Lambda x transpose x, sorry, x conjugate transpose x. Okay? And another thing, x transpose q x conjugate is equal to x transpose q transpose x bar. Is equal to x conjugate transpose q x lambda x conjugate transpose x, also lambda x transpose x conjugate. Okay, from here and here, and also from here, we can conclude that lambda conjugate x transpose x conjugate is equal to lambda x transpose x conjugate. Since we assume that x is not equal to 0, we can conclude that lambda conjugate is equal to 1. So, S is real. Okay. Okay. Another thing to mention is if a scalar matrix Q is positive semi-definite, then its eigenvalues are non-negative, which is greater than or equal to 0. Let's prove it. Let's say this lambda is eigenvalue of Q. And since this is eigenvalue, we can write it as 2x is equal to lambda x for some non-zero x. And since we assume that Q is positive semi-definite, x transpose Q x, which is greater than or equal to 0. And this is exactly the same as x transpose Qx is equal to lambda x. And lambda is a scalar value. We can put that lambda in front of this lambda x transpose x. We know that this is a square of a vector. Right? But not exactly the same. Okay. Anyway, this is a scalar term, so that is non-negative term. But non-negative term times lambda should be greater than or equal to 0, which means this lambda should be non-negative. Okay, that's the end of the problem. You guys are supposed to remember or memorize all these propositions. Without it, you will be in some trouble in solving some kind of equation. Okay, you got to know all the properties of this. Okay, another very important thing is another proposition. Okay, if Q is symmetric, then Q is equal to R, D, R transpose, where R is an orthonormal matrix. The columns of R are an orthonormal basis of eigenvector of Q. And D is a diagonal matrix. The corresponding eigenvalues of Q. Okay, the important thing is if Q is a scalar matrix, Q is symmetric, then you can decompose this Q into R, E, R transpose, which is R is orthonormal matrix, and the columns of R are orthonormal basis of the eigenvalues, and D is the diagonal matrix consists of eigenvalues. That's a very important characteristic of this square symmetric matrix. Okay, for the information, this R and D are square matrix. Okay. Okay, cool. Let's assume R as described here. So we can write R is U1, U2, Un. These U are not scalar. These Ui's are a column vector. So actually this R is n by n square matrix. Okay? Where this Ui's is U1, U2, Un are the n orthonormal eigenvectors of Q. This is exactly the same statement like this. autonomous basis or autonomous eigenvector. Right? And let's assume B is the diagonal matrix with eigenvalues. All other terms are 0, where one, 2, n are the corresponding eigenvalues. Okay, then we can deduce some kind of property like this. R transpose R is also a n by n square matrix. However, if you look the component of this R transpose R matrix, right? We assume that this R consists of U1, U2, U3, Un. Even though this U is a column vector, right? We put this R right here. Okay? If you do R transpose R, this is going to be this UI and UJ are also column vectors. So this is not a scalar vector, it's an n by n matrix. However, this is true. Right? And since we define this orthonormal eigenvectors, orthonormal, which means they're orthogonal and the sides are normal, so it's 0 and 1. Okay, if this is the I is that's the definition of orthonormal vectors. Okay. So based on this information, we can easily deduce that this R transpose R matrix is nothing more than identity matrix because of this property. Okay? And another thing is therefore you can have R transpose equal to R inverse. Okay? And also we got to note that this lambda I times R transpose UI is lambda I EI, where I is 1 to n. This EI means unit vector in I direction, in n dimension. Okay? Okay, therefore, this R transpose QR is R transpose Q. Instead of R, I take from this 1, 2, n. Is, we can multiply one by one, which is equal to R transpose lambda 1 u1, lambda 2 u2, lambda n un. Okay, and from this property, lambda is a scalar, so it can be here or there. So this one is nothing more than just diagonal matrix. Which is equal to D. From the property number 1 and 2, so Q is equal to T right? This one is equal to D. So we multiply inverse of R transpose inverse of R here. So we will get this, which is using the number 1, which is R. So end of the proof. Okay. Okay. Since we don't have much time, let's proceed to another division. Okay. Another one. If Q is positive semi-definite, then Q is equal to M transpose M for some matrix M. If Q is a square matrix and also positively semi-definite, then there is just some M matrix, and we can decompose our Q matrix into M transpose M. Proof. If Q is positive semi-definite, we already showed that this is R, B, R transpose. And R, B is the diagonal matrix with eigenvalues, and this R is eigenvectors, matrix of eigenvectors. And we can rewrite this one as R, B, F, B, F, R transpose. Okay? And we know that if B is a diagonal matrix, T transpose is B. Right? So this is M transpose N, where N is equal to so N of proof. Okay, next thing, next proposition. If Q is positive semi-definite, then X transpose QX is equal to 0 implies QX is equal to 0. Okay? This means if this is true, then this is true. Okay. X transpose Q times X transpose X is equal to 0. And since Q is positive semi-definite, we can utilize that one to replace Q here. Right? And this is exactly the same as Mx, P, Mx. Which is the norm of this Mx squared. Which implies if this norm of Mx is equal to 0, which implies Mx is 0, which implies, we did that one, which implies Qx is equal to Mt Mx. Right? Because we assume that Q is equal to Mt Nm, and since this is 0, this is 0. And therefore, okay. Another proposition. Suppose Q is symmetric. Then Q is positive semi-definite and non-singular if and only if Q is positive definite. Okay. For that part, we have to prove in 2 steps. First thing, we have to prove this step. Q is positive semi-definite and non-singular, then Q is positive definite. We are going to define first prove that direction and then that direction later. Okay, suppose X is non-zero, then X transpose QX is greater than or equal to 0 because Q is positive semi-definite. And also, if x transpose qx is equal to 0, then from this proposition we just proved, qx is 0. Which is contradiction, since q is non-singular. Okay? Thus, x transpose qx should be greater than 0, excluding equal to 0. So, q is positive digit. Okay? The other way around. If q is positive definite, then q is positive semi-definite. It's very straightforward. If q is singular, then qx is equal to 0. This qx has a non-zero solution, whereby this x transpose q, x is 0 and x is not 0, and so q is not positive definite, which is also contradiction. So from these two, we just prove this. If q is symmetric matrix, then q if q is a positive semi-definite and non-singular, if and only if q is positive. Okay, another proposition. Suppose q is symmetric. If q is positive definite and there is another matrix which is q, c transpose d, then n is positive definite if and only if D is greater than C transpose Q inverse D. Since Q is symmetric, this N matrix is also a symmetric matrix. Okay? This is what we call submatrix. Suppose D is suppose D is less than C transpose Q inverse C, and that is X is equal to minus C transpose Q inverse C. Oh, sorry. X is minus C transpose Q inverse, comma 1 transpose vector, right? Then X transpose N X. What we have to do is just apply this X and N matrix. And if you do your math, you will have C transpose Q inverse C minus 2C transpose Q inverse C plus B. Okay? And C transpose Q inverse C minus 2 of C transpose Q inverse C, which is minus C transpose Q inverse C plus D. But we suppose that this is true. So this is true. Sorry. Thus, N is not positive degree. Okay, conversely, suppose B is greater than C transpose Q inverse C, and let X is equal to Y comma Z, then X transpose NX is equal to, also if you do the math, this is Y transpose Q Y plus 2Z C transpose Y plus BZ squared. If X is non-zero and Z is equal to 0, and X transpose NX is Y transpose QY, which is greater than 0, since Q is positive definite. If Z is non-zero, we can assume, without loss of generality, that Z is equal to 1. And so, X transpose NX is equal to Y transpose Q Y plus 2CT Y plus D. The value which minimizes this form is Y is minus Q inverse C. And at this point, this Y transpose Q Y plus 2C transpose y plus b is minus c transpose q inverse c plus b. Based on that, greater than 0. And so n is positive definite. So this completes this proofs. Okay. And according to the lecture notes, there is a one more proposition to the proof, which is, suppose Q is symmetric matrix, then Q is positive definite if and only if all leading principal minors are positive. And I strongly ask you to prove by yourself. Okay? After 5 minutes of break, we will continue on this optimization algorithm. And I'm very sorry that I'm not going to scare off you using this all these hardcore mathematics proofs, but I think this is the very basic we got to know before continuing to optimizing the algorithm. Okay. Steepest descent algorithm for unconstrained optimization. Okay. The unconstrained optimization problem P is defined as minimization of some objective function such that, right, where fx is differential. Okay. Give x at x bar a point, a direction D is called a descent direction of f. And x bar. If there exists non-zero delta such that fx bar plus alpha b is less than fx bar, or alpha inside of this zero delta. Okay. Let's think of a contour. And this is the highest point. Sorry, lowest point. So it's a well-defined differentiable surface function. Okay, let's say this is x bar. And at this direction, you have many directions all around this 360 degrees. There are lots of directions. But we call descent direction D if there exists a very small distance delta, such that if you follow that direction in very small amount, then you will actually the smaller value than your original position. That's the definition of this descent direction. Okay? This is the control line. So if you this direction, how about this one? Is it true? Those points should be x plus alpha d, right? That point. So f is compared to your original position's x. Decrease. Then D is descent direction. How about that direction? How about that? It does not hold anymore. Okay, so that is not descent direction. Okay? How many descent directions are there? Many, unlimited number of, any direction in this area, okay, are all descent direction. Okay? Okay. So gradient f x bar transpose E. Gradient at fx bar is right. That's the gradient. It's a function with increasing direction, mostly increasing direction. That's the gradient. So, inner product of this gradient at fx bar with this E. If this is, it's always defined as if the inner product of this gradient vector with this direction D is less than 0, which means this is gradient, this is the tangential line at this contour. So if D is in this region, then this dot product will be greater than 0. If this T is within this region, then this dot product is less than 0 because the angle is greater than 90 degrees. So that's the definition of descent direction. Any question? Okay, that's the concept here. And this title implies that there are, among these numerous many descent directions, there are steepest descent direction. The direction where this function decreases mostly. Okay? So anyway, in our optimization problem, especially the minimization problem, the thing is, if we keep following this descent direction, we will eventually get to local minimum, right? That's true. But why steepest descent direction? It's because if we follow the steepest descent direction, we can arrive with local minimum fast. Okay? We want to arrive at the local minimum and we want to arrive with fast. That's why you take a stick to distance direction. Okay. The stick to distance direction moves along the direction, and usually for the mathematical convenience, we usually take the direction with this magnitude is equal to 1. Then minimize the function, and usually this steep twisted distance direction is usually the opposite of the gradient. To make the unit vector, we do this. Okay? And if this is too complex, you can just use just a steep twisted descent direction. Okay, question. What if this gradient at a certain point is 0? Is it possible? Yeah, it is possible. Are there any steepest descent direction? No. Right. If you got that value, you will be in local minimum. You are already there. Okay. Okay, let's do this algorithm. Step 0. Given an initial point x and set k is equal to 0. It's for the initialization. Step 1. Okay, find the steepest descent direction. If dk is 0, then stop, because you are already there. Step 2. Choose step size alpha k by performing an exact or inexact line search. In another word, solving alpha k dk. Okay, choose the step size alpha k by performing an exact or inexact line search, which is another meaning. It's just a mathematical notation. Alpha k is when this variable is alpha, minimize the alpha which minimize this one is your alpha. Argument minimize alpha f x bar plus alpha dk. That's the meaning. Step 3. Set xk plus 1 sk plus alpha k dk and k plus 1. And then go to step 1. So, if you do follow this one, you can actually solve this unconstrained optimization problem utilizing statistical descent algorithm. Okay. So, question: can you write a software, the MATLAB code to do this, or C++ or Java or whatever your choice of language? And my recommendation is MATLAB, and the next homework is about writing a code using various algorithms. Okay? Okay. Let's say there is also a contour like this. And we'd like to minimize it, and this is the global minimum, and this is the two local minimums. Okay, first thing, given x0, and you initialize the counter as a 0, there is no nothing. You have to just guess it at the first location. So this is my guess. So this is x0. Okay? And then the next step, I have to calculate the steepest descent direction, which is, since this is the tangential of this control line, this is going to be minus my steepest descent direction. If at this point, if gradient is equal to 0, then I have to stop. Okay? Step 2. I set the direction here, but how much do I move? That's the problem. The best possible scenario is, if you start here, you can go just until here. Right? And first step. But these are your step size. And you have to solve it. How much do I have to move? Okay? Anyway, for now, let's assume that you just solve it and you move until I get here. The next step is make this point, x0 plus alpha 0 b0 is x1. Let's move this is x1. And increase of your counter by 1. Okay, then we go to step 1. Okay, and maybe this is your steepest descent direction. And define another step size like that, and this is your x2, and maybe in 3 or 4 steps you will arrive at local minimum. Okay? The thing is like that. If you choose this is your x0, then your steepest descent direction is here. may end up with just one step into a global minimum. But there is no specific way to do that. It's just by pure luck. And as you can see, if it goes to the local minimum, or is it going to do global minimum, we don't know. It's just another guess. So this is pure guessing. You have to throw the dice. Okay? Okay, let's think about this step number 2. Okay? Since this is a curved surface, and let's assume you cut this surface and look from this direction. Okay, then the shape will look like that, right? We are in here, x0, right? And this is y, right? X is pointing here, because I just assume that this is perpendicular to this x direction, right? I just cut this surfaces here and looking in this direction. And you know this is B0, steepest descent direction here. And all we have to do is following, we want to go there. And we want to decide how much we want to decide alpha 0. Right? So another thing is solving this sub-optimization problem, one dimension, is the meaning of this statement. Alpha k is equal to argument which minimizes x bar plus alpha 0 b 0. Okay? Question? Okay. Let me ask a question. Can you easily solve this alpha 0? Yeah, why not? As long as you can easily evaluate fx. But sometimes evaluating fx is really, really important. For example, if fx is a function like that, the maximum response when your maximum heave response when your vertical length is x. Where they're approaching some kind of waves. In order to calculate it, you have to run a floating body analysis for each x point. There is no single and nice equation for that. You have to choose one value here and do an evaluation, which will take a couple of hours, and then you can plot it. And if you change a little bit of x, and you do another 3 hours of simulation, and you can plot it. And do it again. So usually, people do optimization problem when there is no nice single equation. If there is a very nice and simple equation, it's much better to just solve the equation. But sometimes, like cost of CCS chain cost or something like that, then if you choose one temperature or pressure, then you do all the evaluation and you can just give the cost is something or like that. So, bottom line is, evaluation of FX takes lots of time and very expensive. Then, can you still solve this one? Yeah, there is some way to do that. Okay. Have you ever heard of the line search? Line search. Okay. Yes.
If the diagram, if I see the diagram, to searching the programming of the essay, maybe you explain only the ideal case.
Yes.
If I see we start on the initial point x0,
Yes.
we can go to the two passes. The one pass is the right way, but in another way we can go to the wrong way.
Why?
In that case.
It is possible. You can go whatever direction you can.
Yeah, but how we can check our direction is right or wrong during the calculation?
Oh, okay. There is this is the simplest possible algorithm to solve the unconstrained optimization problem. Just following the sequence of this integration. And each path is a limit. Okay? And in order to overcome those kind of limitations, there are numerous other algorithms to solve this unconstrained optimization. And it will come later. Anyway, got to understand this. Okay? Let's assume there is some thing like this. As I mentioned before, evaluating function and drawing this kind of thing is really time consuming and expensive. So if it's not, we can just take as much as possible sample point and evaluate multiple times, and it is just easy to draw this kind of graph like that. But this is not possible. So the thing is, we just conjecture it. For example, here we know the function value, and then what we do is there is one of the inexact line searches, the bisection search. Okay, but take a randomly chosen range. Okay, and then evaluate that one. Okay, and take the middle and evaluate that one. And you compare it with. Okay, then you can tell which section you should go. this one or this one, and then you do that again. You do that again. If you take this one, then also take the middle. Take the middle, take the middle, 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 and something like that. That's a bisection. Or there is a golden section. Bisection, you take the half of the range. Golden section, you take the golden ratio of the chain, the range. So 0.33, something like that. And you take the 2-point range. And there is another search method to actually find this one. And the point of this search algorithm or line search is that minimize the number of variables. Okay, that's it. We will discuss about this line search and other things in next classes. Okay, one thing to consider is previously we talked about some weird things like open set, convex set, existence of the global, the local optimization things and something like that. This is really important because, for example, this is convex function. And we know that if we know, even though the evaluation of the function is not the last time, but if we know, even though this function is very hard to evaluate, if we know this is convex set, then we can apply one of our propositions or theorem to more easily calculate this optimum based on the property of the function. Okay? Or if the function itself can easily approximated by the quadratic form, which the Q, matrix Q comes in. If the function's quadratic form has the Q matrix, and this Q matrix, Hessian matrix is positive semi-infinite or has some kind of very nice property, then we can alleviate the time-intensive evaluation. We can more cleverly choose or cleverly reduce the number of evaluations. Okay? Also, one more thing to mention. Let's assume this is your question. The x, height of x. What's the, and x is the, at this point is the maximum pitch response. And you want to minimize the pitch response by cleverly, adjusting the x. Well, if you choose initially a random x, then you can do the Womit analysis to calculate the pitch analysis, pitch response, and that's one thing. You need at least one simulation. Okay? How about gradient? How can you calculate this? We don't have any nice mathematical function. Well, you need to evaluate at least two very close to each other, and you can calculate the slope of the function. So, if nothing is nice, you have to evaluate at least 2 times from your function. For example, if your Womit analysis takes about 3 hours, in order to calculate a gradient at point, you need at least 6 hours. How about Hessian? to calculate the Hessian. Basically 4 times. You know, you got to have 2 points to evaluate a slope at the point. You got to evaluate another slope, and you can calculate the change of that slope. So Hessian requires at least 4 of your evaluation time, which is 12 hours of one analysis. Because that's the usual case in optimization problem, people want to develop numerous type of optimization algorithms which minimize the function evaluation, which minimize utilization of Hessian matrix. One Hessian requires 4 evaluation. If you reduce one Hessian evaluation, you can reduce 4 types of function evaluation. Also, people want to remove the evaluation of the gradient. If you remove this, you can eliminate 2 types of function evaluation. But this simplest algorithm, steepest descent algorithm, for one iteration, at least you have to evaluate 1 time of gradient and 1. Okay, so that's a kind of very simple and kind of efficient search algorithm. Okay. When it comes to the computer software, you have to be very careful because that's not the usual case. What if your evaluation is 0.00001? Are you willing to continue? It depends on. So usually they introduce a very small epsilon value. What they do is something like that. If gradient value is really very small, then you stop. But sometimes this can be a vicious thing in your search algorithm. For example, let's say not 0 here, but very small value. But when from here you arrive just here, then if you choose the wrong epsilon value, you will end up here, nothing. So everything has some pros and cons. Think of it. Okay, let's continue to this line search from this Wednesday. Thank you.